Okay, so let's finish what we started yesterday with Laplace transforms. So, revisiting this nice graphic that's showing how it is that we actually apply this process of finding a Laplace transform to an IVP to help us actually solve a differential equation. So, how does this work? Um, so, I have IVP I start with. So, IVP is some differential equation. Ly is equal to right-hand side function plus initial conditions. I hit that with Laplace transform. As we'll see, this always results in algebraic equation that looks like this. Okay, where P of S is characteristic polynomial. Big Y of S is the Laplace transform of our unknown function y. Q of S is something that's, I'm not even going to say anything else. It's just some expression. Big F of S is the Laplace transform of little f. As it turns out, in this entire process, typically, like on average, the worst part of it is finding big F. Okay. Now, for a lot of the examples, in fact, for most of the examples I do today, finding big F is not going to be that much of an issue, but typically, in general, for a completely general problem where you're applying Laplace transforms, big F is the thing. We'll be posting quizzes and answers as practice as originally planned. Yeah, so I haven't done anything like that. So what I thought was, well, the online notes has fully worked solutions already. So that's a ton of practice as it is, in addition to any of the GSS sections and office hours. So no, I don't plan on posting any quizzes with worked answers or whatever. Like I said, in lieu of that, you have work solutions in the online notes. Okay, so getting back to this, like I said, finding big F is typically the worst part of all of this. Once you've done that, though, you have an algebraic equation. Solving for big Y of S, this is not even really a thing, right? Going from here to here, you could have done that before you'd ever set foot in a differential equations class. So I have an expression here. So once I have computed what big F of S is, Q of S is always going to be easy to find. And this P of S is my characteristic polynomial. I have big Y of S is this expression. Big Y of S, remember, is the Laplace transform of my unknown little y solution of this differential equation, my unknown function that I'm trying to find here. Right? And so I have the Laplace transform of my solution is this thing. And in order to go from Laplace transform of solution to solution, I have to hit this Laplace transform with the inverse Laplace transform, which takes me back. Okay, and that's the whole process. Now, I'm going to work through 3 examples that take you through this part of the process that will take me to here. And then I'm going to talk about the inverse Laplace transform, and I'm going to do it for each of those examples in a row. Okay, so like I said, the first 3 examples I'll work through will be me doing this part of the process, and then the last step I will do all at once after I've done those 3 examples. So this splits up my practice into 2 parts: finding Laplace transform of solution, finding inverse Laplace transform. It turns out that this inverse Laplace transform is, once you're used to it, this is not so bad, because if the Laplace transform going forward amounts to using properties of Laplace transform and reading entries off of a table, the inverse Laplace transform, as we'll see, is just reading the table backwards. Okay. It will probably take me the full time to do these 3 examples, but we'll see. I'll try to do as much as I can. Okay. So the examples in question. So first of all, let me go. Where's my first example? There it is. Okay, so first of all, example. Find the Laplace transform big X of S for the solution little x of t to the IVP, which is given as the following. X double prime minus 2x prime minus 8x is equal to 0, with initial conditions x of 0 is equal to 3 and x prime of 0 is equal to 7. Okay. Now, I'm going to be making reference to several sheets that I drew up last time. Okay, so let's have a look at those really quickly. So first, just to remind you, the first step in this process is I start with IVP and I hit it with the Laplace transform, use the properties of the Laplace transform I know and the tables to come up with an algebraic equation that looks like this. I solve that algebraic equation, that part's easy. And then I should be done for this, because right now I'm only asking for the Laplace transform. I'm not asking to actually solve this using Laplace transforms, okay? So recall there was a couple of things. When you had some unknown function, in this case little y, we use the notation that the Laplace transform of our function little y is big Y. The Laplace transform of little y prime is then s times big Y minus little y of 0. And the Laplace transform of little y double prime of s is s squared big Y of s minus s y of 0 minus y prime 0. You have to do this. You have to use these three facts in every single one of these Laplace transform problems. So let's do that now. Okay, so first step in the process is to hit both sides of this with the Laplace transform. What does that mean? That means that I take the Laplace transform of the left and that is equal to the Laplace transform of the right. Okay. Well, the Laplace transform of 0 is easy enough. It's going to be 0. Remember, by definition of Laplace transform, it's just integration of the function in question against this parameterized, this e to the minus st business, right? But you're integrating against 0, so that's clearly 0. And so for a homogeneous equation, this is no problem. Now, I know what you're thinking. You're probably saying, okay, this is a homogeneous equation. Why would I ever think to use Laplace transform on this? The idea here is the idea with anything like this. You want to first check, whenever you have a new method of doing something, you want to first check that it works for the easy stuff, right? You got to check that it actually works for the stuff you already know how to do. This is like calibrating your method, right? So here, I want to use the fact that the Laplace transform is linear. So what this means is that I have L of x double prime of s minus 2 times the Laplace transform of x prime of s minus 8 times the Laplace transform of x of s, and that is equal to 0. Okay. Okay. Well, let's use these three facts from this sheet. So my notation is Laplace transform of unknown function little y is big Y of s. Laplace transform of little y prime is this thing. And Laplace transform of y double prime is this thing. So using these three identities and the same notation, I have that the Laplace transform of little x of s is what I call big X of s, right? And the Laplace transform of little x prime of s is then what? It is s times big X of s minus little x of 0, but x of 0 is 3. So this is s times big X of s minus 3. Okay. Lastly, Laplace transform of x double prime of s is s squared big X of s minus what? minus s times little x of 0 minus x prime of 0. Okay, but what is this? So this is s squared big X of s minus s times x of 0 is 3s, and x prime of 0 is 7, so this is minus 3s minus 7. Okay. And so, plugging each of these into here, what do I get? I get Laplace transform of x double prime of s, that's this thing. So this is s squared big X of s minus 3s minus 7 minus 2 times the Laplace transform of x prime, which is s big X of s minus 3, okay, minus 8 times the Laplace transform of little x, which is just big X. And that is equal to 0. Okay. All right. So I want to take all of the terms that involve a big X of s and separate them and simplify what's left. So let's do that. Here, this is, so I have s squared x of s minus 2s x of s minus 8x of s. Factoring, what do I get? I get s squared minus 2s minus 8 times big X of s. That takes care of those terms. What am I left with? I have minus 3s minus 7. Minus 2 times minus 3 is plus 6. And that takes care of everything else. That's equal to 0. Okay. Then moving this to the other side and dividing by this polynomial, this means that x of s is equal to, this is minus 3s minus 7 plus 6, so this is minus 3s minus 1, so this is 3s plus 1 divided by s squared minus 2s minus 8. And that was all that I was asked to find. So what do I say here when I'm done with this part? I say, well, the Laplace transform of my solution to this IVP is x of s is 3s plus 1 divided by s squared minus 2s minus 8. Okay, so I'm done. Now, here is something to note. What is this? Well, you recognize this polynomial. This is the characteristic polynomial, P of s. This is the char poly. All right, this is the characteristic polynomial. Look, you can just read it off from this equation. All right, this is, of course, it's with s plugged in, but it's s squared minus 2s minus 8. There it is. All right, so indeed, this is the characteristic polynomial. It always works out like this. So when doing this algebra, what you get here is going to change from problem to problem. That's that Q of s thing. It's going to be different from problem to problem. That's just always going to be different. But this portion of the algebra always has to work out in this way. If it doesn't, then you've done something wrong. So the algebra always has to work out with characteristic polynomial times Laplace transform here. Okay, let me check questions really quick. There won't be a MATLAB question on exam 2. There will be one on the final exam, though. Okay. So we found the Laplace transform of the solution. Okay, so this is the Laplace transform of x of t. So we haven't found little x of t yet. We've just found its Laplace transform. Okay, so we'll call this example 1. Okay, so let's do another. That was a homogeneous equation. That was a little too easy, right? It was a little too easy. Let's do something harder. So here's an example. We'll call this example 2. Find the Laplace transform big Y of S, which is Laplace transform of little y of S, where little y of t is the solution to the IVP. It's the following. So this is y prime minus 2y is e to the 5t. And y of 0 is 3. Oh, sorry. Okay. Now you may say, wait a second, this isn't even a second order, right? This isn't even a second order equation. So is this going to work? Yeah, it's going to work. It's actually going to work for any order. The only thing is that, of course, you know, the thing that you get is going to be more complicated for higher order stuff, just because the polynomials involved are going to be higher degree. But other than that, yeah, this is going to work in the exact same way. Okay. So then, how do I do this? I do the exact same thing that I did for the other case. So I hit this with the Laplace transform. So Laplace transform of y prime minus 2y is equal to the Laplace transform of e to the 5t. And yes, technically there's an s here. I will suppress that sometimes just for shorthand purposes. It's not that big of a deal. So this is my equation after I've hit both sides of the Laplace transform. So my left-hand side, using the linearity, this is Laplace transform of y prime of s minus 2 times the Laplace transform of y of s. And that is equal to the Laplace transform of e to the 5t of s. But what is that? What is this? We can read that off from the table. Right? This was actually the first thing that we computed the Laplace transform of. What is this? This is 1 over s minus 5. I know my s's and 5's are similar. I'm very sorry. Nothing can be done about it. Okay. So this is 1 over s minus 5. All right, is this? Maybe I'll box this so you don't get confused with this equality. So this is 1 over s minus 5. Okay. All right, so in this instance, finding the Laplace transform on the right-hand side wasn't a big deal. Okay, so then, what do? I use the exact same thing as before. So Laplace transform of little y of s, by definition, is big Y of s. And Laplace transform of little y prime of s, using this identity, is s times big Y of s minus little y of 0, but I have that IVP. Now you might be saying to yourself, wait, notice that in order to do this process, I very much need these initial conditions. That's true. So it turns out for Laplace transform stuff, you are applying it to an IVP always. So you're not doing it for a general differential equation. You need the initial conditions. Okay, to actually get something. All right. So here we go. This is s y of s minus 3. Okay. Now, using that here, so this tells me that Laplace transform of y prime is s times big Y of s minus 3 minus 2 times big Y of s. And that's equal to 1 over s minus 5. Okay, continuing on, isolating my terms that involve a big Y of s, I have s minus 2 times big Y of s minus 3 is equal to 1 over s minus 5. Okay. So then, adding 3 to both sides, dividing by s minus 2, y of s is 1 over s minus 2, s minus 5, plus 3 over s minus 2. Right? Slightly off camera there. Move my laptop. There we go. Okay. So again, this is the Laplace transform of the solution to this thing, right? So this is the Laplace transform of the solution to this IVP, which is actually a first order thing. Okay. Explain the property of the Laplace transform. So the property that you're talking about is this. We actually did do this. So basically, we used the fact that this was true to show that, well, y double prime is just y prime prime. So you apply the same fact to y double prime and you get exactly this. So the three things that you need to know about the Laplace transform applied to unknown function is this. By definition, the notation we're using is Laplace transform of unknown function little y is big Y of s. Okay. Now, shorthand way of writing these is the Laplace transform of the same little y function, except you're taking the derivative here, is sy of s minus y naught, right? Y of 0. And then the Laplace transform of its second derivative is this expression, s squared big Y of s minus s times y naught minus y prime of 0. Okay. So that's where the initial conditions come in these problems. Okay. One more example before I talk about the inverse Laplace transform. Okay. So that was example 2. Okay. So one more example. There's something about these Laplace transforms you're going to get a mind, maybe you have already kind of seen an eye for, especially with this one. You're going to see what it is that goes on. And I can predict, I have a crystal ball, I can predict that you're not going to like it, but it's okay. All right, you will manage, you will get over it. Okay. So the third example, find the Laplace transform big H of s. So that's the Laplace transform of a little h function where little h of t solves the IVP. That is little h double prime plus 4h is equal to sine of 3t, where little h of 0 and little h prime of 0 are both 0. Okay. So, quickly, same thing I always do. I hit both sides of this with a Laplace transform. So this equation means that Laplace transform of little h double prime plus 4 times little h of s is equal to the Laplace transform of sine of 3t of s. Okay. So, using the properties of Laplace transform, that it's linear, this is Laplace transform of little h double prime of s plus 4 times the Laplace transform of little h of s. And that is equal to, what is the Laplace transform of sine of 3t of s? So you might remember from the last time, this is b, right? We did sine and cosine of bt. So 3 is equal to b here. So this is 3 over s squared plus 3 squared, which is 9. Right? Why this? Recall that this is from last time, or if you're reading along in the table, that's fine. So Laplace transform of sine of bt, that's a b, not a 6, of s is equal to b over s squared plus b squared. All right, this is either directly from the table or directly from what we computed last time. I don't know why these pages are curling up all of a sudden. This is bad deal. Hold on, let's weight it down. There we go. Okay. All right. So this is just directly Laplace transform of sine of 3t. Now, you might be saying to yourself, hey, in all these examples, it didn't really seem like finding the Laplace transform of this f was too bad. It's not when you can just read it off from the table. But in general, if the right-hand side function is just some general function that's exponential sines and cosines and other stuff, it can be really, really hard to do that part. Yes, in this case, we literally just read it off the table, so obviously it's not bad in this case. But it can definitely be bad, and in general, it will be the worst part of this process. So if you do some of the harder examples in the homework, in the worked exercises in this section, you'll understand. Okay, so this is 3 over s squared plus 9 is my right-hand side here. So again, I'm doing the same thing that I always do. So Laplace transform of little h of s is what I'm calling big H of s. Laplace transform of little h prime of s is, you might say, wait, little h prime doesn't even show up. This helps me remember what it is that's going on here. So this is s big H of s minus little h of 0. Now, little h of 0 is actually 0. So this is just s times big H of s. And then lastly, Laplace transform of little h double prime of s is s squared big H of s minus s little h of 0 minus little h prime of 0. Both of these are 0 by the initial conditions, and so this is actually just s squared big H of s. So returning to my equation after I've hit it with a Laplace transform of little h double prime is s squared of big H of s plus 4 times the Laplace transform of little h, which I'm calling big H of s, and that is equal to 3 over s squared plus 9. Factoring out a big H of s here and dividing, what does this mean? This means that big H of s is equal to 3 over s squared plus 4 times s squared plus 9. And there we go. Okay, so now we've done 3 examples where we have found the Laplace transform of the unknown function that we seek as a solution to the differential equation. Now, what does this mean? Big question, big Q here. Question: how do I go from big Y of s to little y of t? I.e., how do I go from Laplace transform of solution to solution? The answer is the inverse Laplace transform. Okay, that's probably obvious since I've hinted here. This is the inverse Laplace transform. L inverse. Okay. Well, we saw what the definition of the Laplace transform was, but practically, as I said, you're typically just reading off of a table and using properties of the Laplace transform, not actually using the definition. But thinking about the definition here, how would you unintegrate against the function e to the minus st? Right? Well, you're not going to think of it like that. Okay. And so actually the way that you're going to think about the inverse Laplace transform is very simple. Okay. So the question, how do I compute the inverse Laplace transform? And the answer is I read the Laplace transform table backward. Okay. I read the table backward. Okay. So what do I mean by that? If a Laplace transform table is giving you a giant list, so again, I posted in the chat that you can follow that link and go to page 37 is like the absolute like ultimate list. There's also a pretty good list on there's a pretty exhaustive list on page 14 as well. So tables, page 37 and page 14 of 2.9 will do it. These are definitely all you need. This table on page 14 I think is enough. Since that is pretty much everything. So anyway, so looking at the table, if a Laplace transform table is reading each entry in the table, so you can either look along with me on page 14 or page 37 in the online notes. So I'm looking at page 14 right now. If I'm looking at this list of Laplace transforms, each entry is reading from left to right, saying the Laplace transform of the first entry is t to the n, is n factorial over s to the n plus 1. The Laplace transform of cosine of bt is s over s squared plus b squared. The Laplace transform of sine of bt is b over s squared plus b squared. The Laplace transform of e to the at t to the n is n factorial over s minus a n plus 1, right? You can do all those saying that multiplication by an exponential is the same thing as translation, right? So we went over all that stuff. So that's me looking at the table and reading those things off. Okay, so then the inverse Laplace transform is reading backwards. So what do I mean by that? Well, let me pick a particular example. So example of inverse Laplace transform. So example of inverse Laplace transform. So we have the entry in the table. I'm going to use cosine. So Laplace transform of cosine of b of t of s. This is s over s squared plus b squared, right? We saw that yesterday. Okay. So then, how do I write an entry from this for the Laplace transform? Well, I have the inverse Laplace transform. How would I read backwards, right? So I'm saying the Laplace transform is reading left to right, and the inverse Laplace transform is reading right to left. What do I mean by that? You don't need a Laplace transform table and an inverse Laplace transform table, even though the textbook, the online notes, does have a list of inverse Laplace transforms somewhere. Page 16 is their list. Okay, so page 16 is a list of inverse Laplace transforms. Maybe I should write page 16 here if you want to check that out. But the way that you don't really need that at all, and the reason why is if I have a Laplace transform table, well then the inverse Laplace transform is simply me saying the inverse Laplace transform of s over s squared plus b squared of t is cosine of bt. So if the argument for the Laplace transform is this parameter s, the argument for the inverse Laplace transform is this parameter t. Where I apply the Laplace transform to a function of t, I apply the inverse Laplace transform to a function of s. So this is what I mean. And once you've seen that, well, now you know exactly how this works, right? So that's really it. So, for instance, let's just do one more. So Laplace transform of, say, e to the at of s. This, we know what that is. It's 1 over s minus a. So then the inverse Laplace transform of 1 over s minus a of t is e to the at. Boom. All right, we're done. Okay. So, how does this help? So, and why would this process be anything other than straightforward? So here's what can happen, right? I'm just going to jump ahead a bit, and let's refer to this last example I did. So in this last example, I have a big H of S that looks like this. The idea in applying an inverse Laplace transform would be to look at this thing, look at entries in the Laplace transform table. That is, if I'm looking at a Laplace transform table, I'm looking at entries on the right. So I'm looking at entries on the right, and I say, do I see anything like this on the right? And the answer is no, not really. Right? I look at this thing and I'm like, I really don't see anything like that. So what do? Well, the answer is I have to put this in a form that is something like those things showing up on the right. Okay, and that is where the difficulty comes in. So that's where the practice is needed in doing this. If it was just as simple as literally reading off the table, then that would be no fun. So all of the fun is to be had in adjusting these things. So a couple of key facts. What's the most important one? I guess really the most important, I won't say a couple of key facts. I'm just going to say key facts. The inverse Laplace transform is linear. You know what linear means. It means that I can pull constants out of it, and I can pull, and it splits up across things. So for instance, what do I mean by that? Okay, let's just say it. So if I have C, we'll call it big F to keep our notation consistent, plus D big G of S of T. This is C inverse Laplace transform of big F of S of T plus D times inverse Laplace transform of big G of S of T. So it's linear, meaning that I can, if I have something in this form, I can break it apart, right, into these pieces so that I can compute the inverse Laplace transform in these pieces instead. It also satisfies the, I'm not going to rewrite this because you can look at it directly from the table and see that looking at it from the table, a translation in the inverse Laplace transform means going to a multiplication by an exponential, right? So everything that was said for the Laplace transform holds for the inverse Laplace transform. It's just the opposite direction, right? So Laplace transform, multiplication by an exponential gave you a translation. For the inverse Laplace transform, it's a translation gives you multiplication by an exponential. That's it. So anyway, so let's actually apply these to my examples, and then I'll be done. Okay, so return to example 1. Oh, okay. So let me refresh your memory. I have them stacked over here. Here's example 1. Okay, there it is. So we were asked originally to find the Laplace transform of this solution. How do I find the solution? I hit this Laplace transform with the inverse Laplace transform. So returning to example 1, what this is me asking is solve the IVP. I'll rewrite it. It's x double prime minus 2x prime minus 8x is equal to 0, with x of 0 being equal to 3, x prime of 0 being equal to 7. Recall that the Laplace transform of my unknown function that I'm trying to solve for was 3s plus 1 over s squared minus 2s minus 8. Okay. All right. So, what do I do here? In order to find little x of t, all I need is to compute little x of t is actually the inverse Laplace transform of big X of s of t. That's it. So all I need to do is to compute the inverse Laplace transform of this. Okay. Well, how do I do that? I look at the table. So again, I'm going to jump to page 14. Going to look at that table, and I'm going to say, is there anything in the table that looks like this? No, right? There's nothing in the table that looks quite like this. Okay, well, maybe I can try to do something here. So what's something you notice you can immediately do? This characteristic polynomial actually factors. And so note big X of s is 3s plus 1 over s minus 4 times s plus 2. Okay. Is there anything like this in the table? On the right, if we're trying to compute the inverse Laplace transform, we're looking at entries on the right. We're saying, is there anything on the right, on the table, or in the table, that looks like this? The answer is no. Okay. So even though I factored this, I'm still no good. But what if this thing was equal to, say, a over s minus 4 plus b over s plus 2? If this were the case, where a and b are constants, is there anything in the table that looks like 1 over s minus 4. Why do I say 1 instead of a? Well, if a is a constant, then if I'm computing the the inverse Laplace transform of a over s minus 4, I can pull a through that inverse Laplace transform because it's linear. So I can pull constants through it. And so really, I don't care that much about the a or the b here. All I care about is the 1 over s minus 4 and the 1 over s plus 2. And the question is, if I look at the table, is there any entry in that table that looks like 1 over s minus 4 or 1 over s plus 2? The answer is yes, right? Looks like exponential stuff. Well, then we'd be fine. Well, can I make this equal to that? Yes. Yes, indeed I can. How do I do it? Partial fractions. So, you gotta know partial fractions decomposition. Okay, there's no avoiding it. If you have forgotten how to do a partial fractions decomposition, you have to learn. You have to relearn, rather. You gotta refresh your memory on how to do this. So I'll do it in this case, but the other partial fractions decompositions, I'm just going to do them quickly. So how does doing partial fractions work? Remember, there's a lot of rules to set it up. If you don't set it up right, the algebra won't work out. So by partial fractions, so 3s plus 1 over s minus 4 times s plus 2, we seek an a and a b that satisfy this. So then what do you want to do? You want to clear denominators here, right? This is the way you can think about it. There's some shortcuts when it's when it's a simple thing like this. So if you learn to do this using one of the shortcuts, you can absolutely do that. The shortcut, of course, isn't guaranteed to work depending on the algebra involved, and for some complicated examples, the thing that you think of as a shortcut is not it won't work. But in this case, you could do it. But anyway, clearing denominators, what I get that 3s plus 1 is equal to, if I multiply both sides by s minus 4 times s plus 2, this is a times s plus 2 plus b times s minus 4. And then I continue on. So this is 3s plus 1 is as plus bs, so that's a plus b times s plus 2a minus 4b. And so from this I compare coefficients. So I get a system of equation a plus b has to be equal to 3. Coefficient on s is 3 here. So a plus b has to be equal to 3. And 2a minus 4b has to be equal to 1, right? So the constant coefficient here has to be equal to the constant coefficient over here. So you get a system of equations that I can solve really quickly. So doing that, what do I get here? So a is 13 over 6, and b is 5 over 6. I believe is what you get here. Yeah. Okay. Yeah, so 18 over 6, 3. Yeah, that's right. Okay, so this is my a and this is my b. So x of s is 3s plus 1 over s minus 4 times s plus 2, which we've seen is 13 over 6 over s minus 4 plus 5/6 over s plus 2. Hitting this with the inverse Laplace transform, this means that little x of t is the inverse Laplace transform of big X of s of t. I'm going to go ahead and do the linearity here. So this is going to be 13/6 times the inverse Laplace transform of 1 over s minus 4 of t plus 5/6 times the inverse Laplace transform of 1 over s plus 2 of t. Well, now I look at the table, and indeed, if I look at my Laplace transform table, 1 over s minus 4 is right there. What is it? It's e to the 4t. 1 over s plus 2 is also there. It's e to the minus 2t. And so what I get here is that this is 13/6 e to the 4t plus 5/6 e to the minus 2t. And that's it. Okay. Couple of things to note. All right. First thing to note is that this actually is the solution to the example in question. The example in question was a order 2 homogeneous equation. It had characteristic polynomial s squared minus 2s minus 8, which factored and had roots 4 and minus 2. You know from the recipe for homogeneous second order equations that the homogeneous solution, right, or in this case the general solution, is going to be c sub 1 e to the 4t plus c sub 2 e to the minus 2t. Okay, well, that is exactly what you get. The other thing that I'll draw your attention to is the fact that I didn't have to solve for these constants. They automatically popped out. And that's always how it's going to work. So with Laplace transforms, for an IVP, you got to find the general solution, then you have to plug in the initial condition, and you got to take its derivative, plug in the other initial condition, and you got to do some algebra to find those constants. Here, the constants just came with the solution. And that's how it's always going to work. So in this sense, Laplace transforms are actually kind of convenient. Not for an equation like this, but this is going to be true even for harder stuff. Okay. Yes, partial fractions. I am sorry, but there's no getting around it. You gotta do partial fractions decomposition. So now you know what was talking about when I said there was a part that was coming up that you weren't going to like. Okay, so return to example 2. Okay, so find the solution to the IVP that was y prime minus 2y is e to the 5t, and we had y of 0 is 3. Okay, so find the solution to this IVP. Okay, so we found that the Laplace transform of the solution, big Y of s, was 1 over s minus 2 times s minus 5. Man, my s's and 5s. Okay, plus 3 over s minus 2. All right. Okay. So, thus the solution is little y of t, which is the inverse Laplace transform of big Y of s of t, which, going ahead and using linearity, this is inverse Laplace transform of 1 over s minus 2 times s minus 5 plus 3 times inverse Laplace transform. I know I didn't write the t here. Forgive me. Of 1 over s minus 2 t. We know how to do this one. How do I do this one? I look at the table. I don't see anything like this. What's my first instinct? Partial fractions. Okay, so again, use partial fractions to split this up. I'm not going to go through that process here. I'm just going to write down the result of doing that. So using partial fractions here, what do I get? I get that this is the inverse Laplace transform of, using partial fractions decomposition, this turns out to be 8/3 over s minus 2 plus 1/3 over s minus 5 of t plus 3 times, what's the inverse Laplace transform of s minus 2? I know what that is already. That's e to the 2t. So this is 3 e to the 2t. Okay. Using linearity for the inverse Laplace transform again, this is 8/3 inverse Laplace transform of 1 over s minus 2 of t plus 1/3 inverse Laplace transform of 1 over s minus 5 of t plus 3e to the 2t. Okay, and now I can read these off from the table. So from the table, this is e to the 2t, this is e to the 5t. So this is 8/3 e to the 2t plus 1/3 e to the 5t plus 3 e to the 2t. So I can combine these slightly. So 3 is 9/3. So this is what, 17/3 or something? Did I do that right? I see. No, I see what's gone on here. So, oh wait. Oh, I see. I'm right, and the solutions are wrong. So, so what this becomes is this is 17/3 e to the 2t plus 1/3 e to the 5t. So then we should just check that this is actually, note, online notes are wrong on this example. Okay, so if you're looking at the online notes for this example, they are slightly incorrect, and you can tell, wait a minute, wait a minute. Oh no, they're not, wait, what? Why am I wrong? Uh, oh, I see. I see. I see. I see. No, no, no. They're not wrong. I am wrong. So, when they did the partial fractions decomposition, they did the partial fractions decomposition for the whole side rather than just for this. So if you do the partial fractions decomposition in this way, this is actually, I see here, this is not an 8/3. This is a minus 1/3. Yes, this is a, here we go. All right, all right, all right. Let's redo this. This doesn't change things too much. So this is a minus 1/3. So this is a minus 1/3, and this is a minus 1/3. Okay. Yeah. So that what results from this is the following. So this is equal to minus 1/3 e to the 2t plus 1/3 e to the 5t plus 3e to the 2t. 3 is 9/3, so this becomes an 8/3 e to the 2t plus 1/3 e to the 5t. So this, there we go. Now we're right. Okay. And again, note how this works. So what is nice about this is that directly from this process, I get the constants. I don't actually have to solve for anything here. Okay, so I directly get constants here. Okay. All right. One more. Return to example 3. Okay. So, example 3, if you remember, let me find it over here in the pile. There we go. So, example 3 had you computing the Laplace transform for the solution to this equation. Okay, so find the solution to the IVP little h double prime plus 4 times little h is equal to sine of 3t. Okay, where my initial conditions are both trivial. Okay, so here's my IVP. Now I found that, previously that the Laplace transform of my unknown little h was 3 over s squared plus 4 s squared plus 9. Okay. As I hinted before, looking at the table, is there anything to do with this? Well, no. There's nothing in the table that looks like this. And so, what do I do? Well, partial fractions again. Now, at this point, you might say, okay, we've had to use partial fractions in every single one of these examples. Is that typical? One, the answer is yes, it is typical. But then another question is like, why? Why does it work out that I have to use partial fractions so much? Because the table is very simple. The table involves low-ordered stuff. What do I mean low-ordered? If you look at the table really quickly, so again, you can look with me at page 14. So if you look at the table in page 14, notice that apart from a couple of examples where you have a t to the n showing up, so ignore that really quickly. Every other entry in the table has a quadratic thing showing up, right? That's the highest you get. So you have a quadratic thing in s in the denominator showing up. And then when you have an e to the at like on its own, like an exponential, then what you get is a first order thing, just 1 over s minus a, right? And so if you don't have this t to the n term showing up, then the highest order thing you get is a quadratic. And so anything you get in your Laplace transform of the solution that is higher degree, you're going to have to view in some ways being built from first and second order things. So first order and quadratic, the linear and quadratic factors. And what that means is you're going to have to break it up in this way. And the only way to break apart things like that is partial fractions. So yeah, I mean, the answer is basically if you get a Laplace transform that is anything, that is not like completely trivial, basically, then you're pretty much almost always going to have to use partial fractions. So let's do that for this example, and then we'll be done, and you'll have seen enough to understand how this stuff works. So my Laplace transform of the solution is this. I need to use partial fractions again. There's no getting around it. So by partial fractions, you can do something neat here, of course. You don't have to follow the complicated partial fractions rules always. Technically, when you have quadratic factors, if you remember when you do partial fractions, you have to write out different things in the numerators for quadratic factors. Here, what I'm going to do, since this is an s squared and this is also an s squared, I'm going to notice that by partial fractions, all I have to do is be a little smart here algebraically and note that, well, I can view this as 3 over something, right? In the notes, I think he uses z. So I can view this as 3 over z plus 4, z plus 9. Where, yes, z is s squared, but just formally speaking, I can do partial fractions on this thing. And what I get when I do that is 3/5 over z plus 4 plus minus 3/5 over z plus 9. Okay. So this is what I get. Okay. All right. So I want to rewrite h in this fashion. So h of s is this thing. So 3 over s squared plus 4, s squared plus 9. By this partial fractions decomposition, this is 3/5 over s squared plus 4 minus 3/5 over s squared plus 9. Okay. Now, how do I want to write this in a nice way? The arithmetic that's done when this example is done in the online notes, it's not explained, why it is that this is happening. So I'm going to explain to you why this is going on. I want each of these things to look like something in the table. This isn't just true for this particular example. It's true for all of these, right? Because my only method for computing an inverse Laplace transform is reading from the table. And so if the thing that I have on the paper is not exactly what occurs in that table, right, on the right, then I can't do anything. Okay, and when I see expressions like this, what types of entries in the table am I thinking of? Like, what does this look like? I don't have an s in the numerator, right? So having an s in the numerator would change what I'm about to say here. Right now, I don't have an s in the numerator, I just have constants. So what do I want these things to look like? When I see a term like this, what I'm actually thinking is b over s squared plus b squared. Right? If I had an s in the numerator, then I would be thinking of s over s squared plus b squared. And when I'm thinking of b over s squared plus b squared, what am I thinking of in my mind? I'm thinking of sine of bt. Right? So that's what I'm thinking of here. Okay. So then, looking at this expression, what is it that I want to do? Okay. Well, if this is b squared, here that is going to be 2 squared. Here it's going to be 3 squared. So rewriting this in this way, this is going to be 3/5 over s squared plus 2 squared minus 3/5 over s squared plus 3 squared. And now the idea here, to save myself algebra time. You don't have to do this. You could do this just with the algebra. Like, you could do this arithmetic slightly differently, but this saves you computation time. Of course, that's not that big of a deal for the exam coming up since you're going to have days to do it, but still, this is what you can do. So this is s squared plus 3 squared in the denominator. What do I want here in the numerator? I want a 3. Well, I have a 3 in this numerator, right? I have 3/5. So I could rewrite that as 3 times 1/5 and pull the 1/5 out. And that's exactly what I'm going to do. Here, I don't have a 2 showing up, so I put a 2 in, but then I have to put a 2 in the denominator to account for it. So saying that this is going to be 3/10 times 2 over s squared plus 2 squared. Right? Minus 3/5 times, I want to get rid of this stuff. This was purely for exposition. So this is minus, sorry, not 3/5. This is 1/5 times 3 over s squared plus 3 squared. Now I'm ready. Okay, now I'm ready. So, little h of t is equal to the inverse Laplace transform of big H of s of t, which, using linearity, is 3/10 times the inverse Laplace transform of this. We've set it up so that we can read it off directly from the table. That's the point. So reading this off directly from the table, this is sine of 2t minus 1/5 sine of 3t. Again, set up so that we can read it directly from the table. Again, note, no further computation is needed. When you're done with this step, the arbitrary constants have been found and you're done with the problem. That's how it goes. Okay, so let me see what's going on here. What page are these on in the notes? So, I mean, these examples are on different pages, but they're in that page range. I think the last one I just did finishes on page 18. So pages 1 through 18 covers exactly what I did. Can we solve these equations without Laplace? All of these are doable without Laplace. There's something that is like much easier with Laplace, which is piecewise forcing functions, but due to the shutdown and lack of time, we're not going to get into that. Normally in a semester we would have gotten into that, which is exactly something that Laplace can do. But here's the thing, when it comes to Laplace transform problems, it's the only instance in this whole course where I'm going to ask you specifically to use Laplace transforms. So I'm going to give you a problem that maybe you could do it in another way, but I want you to use Laplace transforms to do it. Okay. How did I transform the 3/5 into a 1/5? I just left the 3 behind, right? So this was 3/5. I just left the 3 in the numerator and moved the 1/5, right? It's the same thing. You could view it as moving the 5 to the denominator and then putting it outside. Yes, this is on the exam. Laplace transforms are on the exam. It's the last thing on the exam. So the exam is completely exhaustive on chapter 2. Everything in chapter 2 will be on there. So there will be a Laplace transform problem on the exam. So maybe I ask you just to compute the Laplace transform. Maybe I just ask you to solve it using the Laplace transform. Maybe I ask some combination of those things, but that's the idea. Okay. And so that's it. That's all of chapter 2. So starting next week, we will begin the last chunk of the material, which is linear systems. It will be truncated slightly again due to the shutdown. It will be cut slightly shorter than it normally would be, but we're going to hit all the important stuff. So your final exam is going to be cumulative, and your final exam will include topics from everything. Okay, so the final's cumulative. It's not just chapter 3. So final is cumulative. We're going to cover absolutely everything on the final exam. Okay, so that is it. I will post your exam tomorrow evening, and it will be due Tuesday at some time. Maybe so that people aren't freaking out during lecture. I'll have it be due by lecture time or something. So maybe I'll have it, be due at like I don't know, sometime on Tuesday. So you'll have quite a bit of time to work on it. Like I said, it'll be posted tomorrow, and you'll have all weekend to work on it. If by Professor Livermore's problems you mean the problems from the online notes, definitely. So the online notes are good because they have fully worked solutions, so they're a good way to practice. How many questions will it be? It doesn't matter. It will be long enough to test everything. So the question, how many questions doesn't matter anymore because there's the grading is going to be done differently amongst the TAs than it normally would have since everybody's at home. Yep, mass springs on there. Everything from chapter 2 is on there. So yeah, mass springs on there, Laplace transforms, everything. Well, like I said, you're gonna have days to work on it, so it won't shock you. You'll see what's on it, and then you'll have plenty of time to work on it. So anyway, yep, variation of parameters on there too. You can use it whenever you need to use it. So yeah, that's variation of parameters is definitely on there. Green's functions could be on there. So everything we did in chapter 2 is on there. But yeah, anyway, so that's it. That's all the chapter 2 material. So I will post it at some point. I'll let you know when I do. I'll send out an Elms announcement and then just a reminder of due date and stuff. I'll let you know when I want it to be due on Tuesday. And you will. I will give you submission directions. So anyway, so that's the deal. And I think I'm just gonna have you submit it directly through Elms rather than emailing your TAs or anything like that. So anyway, that's the stream. So I will see you all on Tuesday where we'll start chapter 3 stuff. Like I said, I'll post your exam tomorrow. So see you all later.